So today we're going to cover how to use the 6625 through the front panel operation, connecting all the different devices and making measurements in its three main measurement modes, which includes normal ohms, high ohms, and low ohms. Normal ohms is where you use the bridge to source current, and you're measuring typically from about 1 ohm up to 100 kilo ohms. Anything above 100 kilo ohms, you usually source voltage at a bridge, and the bridge can produce up to 100 volts DC to measure anything from about 100K up to 100 megohms. And when you get down below 1 ohms, you're typically measuring low value resistances down to a micro ohm from about 1 ohm down. And you source current again, but you have to source a lot more current to make it an effective measurement. And so we use the range extender to provide up to 300 amps of current. Connecting devices, we'll start with a typical resistance device is a 4-wire device, and many multimeters and resistors that are used, people are quite familiar with them. It has 4 terminals, and essentially you drive your current into the C terminals here, and then you have a potential pickup here on the P terminals. And so to connect a device like this, you would use some of the free scanner channels here with the wires that come in the system. And so come out of the back of the rack, and there's a coil of them here. And so onside the scanner channels, you'll see here they're labeled, and this is channel 14, and this is P1 and C1 that's on this wire. And then this one here is channel 14, P2 and C2. And individually on the wires, you'll see that you actually have C2 labeled, P2 labeled, C1 labeled, and P1 labeled. So essentially you wire them directly at C here. The P's are for potential, so that's your pickup. So sometimes you'll hear sense as the terminology used instead of P. And C is usually your current terminals or 2-wire connection. So we would wire C1 to C1 inside here. And P1, we're going to P1 inside here. And then you have your P2 and C2. You just twist them underneath your terminals like this. And that's your basic connection for a 4-wire device. And so it'll look something like that. Now as well, things like 2-wire resistors or decade boxes, as shown here, they are connected slightly different because you do not have separate C and P terminals. And so when you run into a device that's like this, the way to get the most accurate measurement is, again, to take your wires, and this is why they're grouped in this fashion. You would take your P1 and your C1, and you would join them together here. Because the lead itself can create an effect to your measurement when you make a measurement. So in order to cancel out the lead effects, you want to make sure that your P and your C are separate wires up to as close as possible to the junction of the resistor. So we run them separately as a 4-wire right up to the point where they join at the lead. So your P1 and C1 come together right underneath the terminal like that. And then you do the same thing on the other side. And what this does is it minimizes the effect of the lead on the value, so you can keep your accuracy. And essentially a 2-wire device would be connected like this. You'll find that most 2-wire devices are usually resistors of lesser qualities, things like decade boxes or transfer standard devices. Or you'll find that a lot of high value resistances from 1 mega ohms and up are typically 2-wire as well. Although they also come in 4-wire for the higher value resistances. Also, when you are connecting devices, we have here a green wire that comes out of the rack, and this is called guard. Now what's important about guard is when you are dealing with devices, here's an example of a 4-wire resistance, the guard, that you tie in here, and what this does is puts the guard on the entire shield of the resistor, and this helps protect from EMI effects and also helps create isolation. Isolation becomes very important and critical when you have a high value resistance because you can get leakages and it will also throw off your results. The part that I want to mention, and it should never be confused, that this is not ground. Guard is actually a live active voltage on the signal, and if you were to connect it to ground, it would actually cause damage to either the equipment you're connecting it to or possibly the system itself. So pay very close attention, because a lot of devices that are active, such as this travel extender here, have both a ground and a guard. And so if I were to connect this here, I must make sure I connect it to the actual guard input when I'm measuring the resistances inside here. This ground here would actually take this voltage signal and drive it straight to earth ground if I were to plug it into here and start the measurement, and that would cause damage to the bridge. So this is very important. However, it's also very important to use the guard, so do not decide not to use it because of the fact you're afraid of making the wrong connection. You just have to be cautious and be aware of what you're doing when you do this. Some instruments will actually have a shorting link between their guard and their ground as well, and if there is a shorting link present between them, you have to remove it. You'll find that becomes an issue with devices like the Fluke 5700 as an example, and we'll actually see that in demonstration as we're going through the plugin for that later. Lastly, moving these devices out of the way, we have the SR1010 here. Throughout a lot of military organizations, they use devices called transfer standards, and this is an example of an SR1010, which is a single transfer standard. They make banks of these that go to SR1030s and SR1060s as well, which can have 3 or 6 of these items all inside a case with oil to stabilize the temperature. And you can see it has a various array of different resistance elements inside it, and you can pick up at any point to get different values throughout this thing. So this becomes very difficult to connect when you're calibrating, because you have to keep moving this connection over and over again throughout here. So we created this device here called the SR1010 adapter, and what it is a series of banana jacks on the bottom which match this pattern, and each of these banana jacks are wired directly onto a scanner channel here, so that through this scanner you can just connect and switch for each one of these resistors. And to install this, you simply just pick the entire unit and you set it on top. You can see here you've got A0 to A12, and on top of the unit you have A0 to A12 here. So this is the orientation you would use here. And then you would line up all the banana jacks like that and press down. We are pressing in a number of banana jacks, so it does take a reasonable amount of force to insert this, as you are actually applying well over 20 banana jacks, so there's a good insertion force required to make sure it's on there securely. And now that it's on there securely, this is shielded to protect from any environmental effects or any contact while the measurements are taking place. And now at any time you can go ahead and just bring up any one of these elements onto the bridge scanner channels. And to take this unit off, these 2 devices here are pressure plates. You push in on them, and this helps you loosen it up, and you can just take it off. That's basically how you connect all of the devices. Again, I had mentioned earlier about the decade boxes. They are a 2-wire device. A lot of labs do a high number of decade boxes, and you would, in these ones, as you can see, you have your host here. You would just twist the 2 wires directly underneath your P1s and P2s. Just insert them together like that. And this one will go in just like that. And essentially, that's how you connect most resistive devices to the system. And once they're present on a channel, you can just measure them through the bridge against your working references here. The last device to connect is a resistance shunt. And this connects, rather than directly to the scanner channels, it actually connects through the range extender, because you have to provide more current. And you can only get up to 150 milliamps from the bridge. So the range extender here will provide up to 300 amps. Depending on the model of shunt you were using, this particular model is a 50 amp shunt. So I can make measurements on this shunt up to 50 amps. Anything beyond 50 amps could possibly damage the shunt. So one would have to take care of the connections. Now the range extender has 3 main taps here. And basically what it is a transformer inside here that steps up the current and changes the ratio of how this resistor is represented to the bridge. And so if I was to connect this, for the one thing I want to look at is what current do I wish to measure at. If I wish to measure at, say, 15 amps, I would measure it on this range here where I can get up to 15 amps maximum, which are just these 2 small terminals here. This particular range here, we can be a times 20 ratio at 3 amps. And one has to look at it and say, okay, well, I'm measuring a very low value, and I'm going to measure, I would most likely measure this one about 30 amps, so I would probably choose this range here, which lets me go from 15 amps all the way up to 30, and it gives it a ratio of 2,000. The importance of the ratio, which we'll get into when we discuss making the measurement, is when you choose a standard up here, the ratio that's defined here lets you calculate which standard you should use to make this measurement. So if I were to make a 30 amp measurement, I would connect it to these terminals here, and you would unscrew the lugs all the way, and you would connect your big current cables right here. You see here it's labeled C1, and so if I make C1, we'll go to C1 on the shunt. And most shunts, the terminals also come out. You'll find that most high current resistances, the types of terminals that are used will either have large knobs or even actually use bolts directly with a ratchet. And this is because when you measure with high current, you need to make sure that the connections are tight. And while making this measurement, I actually made a mistake here, and this particular mistake I would like to point out. And what you see here is while I'm loosening this is rattling. And that's because, if you look at the leads here, you'll see that the leads are one-sided, and you want to push the leads on the inside. And the reason why is that allows for this to twist on a lot smoother. So that mistake is something I wanted to put in here just to make sure that you guys were aware of that sort of thing. And we do the second one properly here. This is for C2. Again, make sure it's good and tight. If you do not get the lugs tight enough, at least a good snug fit, what happens is that the current will actually generate heat right at the connection, and it will basically either throw off your measurements in some cases cause the measurement not to work at all. So loosen this one off. Sideways so you can see it. And essentially, it's connected like that. So these 2 potential terminals still have to be connected as well to make the measurement. And because what's happening is it always takes the 4 wires to make the measurement, you have to use the potential terminals from a given scanner channel. So I will choose this channel here, which again, you read right here, you got your channel 15, P1, C1, channel 15, P2, C2. But because I am sourcing the current from the range extender, the C2s I won't use, I'll just fold them back, because they're not even going to have any power going through them at this point in time. It's just the potential terminals that I'm using to complete the measurement. So again, paying attention to the labeling, use your P1, onto P1, and your P2, onto P2, and then there's your 4-terminal connection there. So again, these wires are not used. There's no current running down them, and that's simply because you're generating current with the higher current extension here, essentially treating this much like a current amplifier. Now, when you have this range extender connected, always make sure you only have one set of leads connected to the range extender. So, although it would be convenient to leave these ones, say, connected here to hook up at any given time, if they were to ever get connected to one another or shorted just by dangling and not being connected to a resistor, then they could also cause damage or throw off your measurements. Likewise, you do not want to leave a resistor connected to this terminal because it will also affect the measurement of this resistor. So you only ever connect the one resistor at a time. So just for the sake of demonstration as well, I'm going to disconnect the large current terminals, because this would be making a measurement from 15 amps and above. If I were to make a measurement below 15 amps, I would connect it in this fashion here. This is again, coming back to the connections on the range extender, here's a connection here at the times 200 range where you can see that the wire comes up from C1 to C1 and C2 to C2. And this range here would allow me to make a measurement, say at 10 amps or 5 amps. It goes anywhere from 3 amps to 15 amps. It's of course, because of the lower current than the 300 amps, it's a much smaller terminal, and the wire gauge is much smaller as well to work with. And essentially, you would do this as well if you wanted to use a measurement from 3 amps and below, down to about 100 milliamps on this range. This is how you connect the range extender. The other thing that's important to remember is that when you're done making a measurement with the range extender, always ensure that you disconnected all cables from the shunt and from the range extender. And this is a good practice to have, primarily because that way you can ensure that you never have two resistance devices or loose cables that can conduct the current connected to the range extender to cause any type of damage or to equipment or to the range extender itself. And as well, when you cycle on the power to the range extender is best powered on under a no load condition, meaning nothing is connected to it. And once it's powered up and stabilized at that point in time, then you can connect whatever you want. But again, maintain one device at a time. And that's how you connect all the basic equipment to the 6625 system, and that's, of course, all the devices that you'll be measuring in the lab. There's a couple other more unique devices, things like the 5700, the Fluke 5500, which we'll discuss directly when we go over the associated software and plugins that go with them, and we'll show those connections at that time. But primarily, these are the devices you will work with on a day-to-day basis. And so now we're going to get into how to make measurements on these devices in normal ohms, high ohms, and in low ohms using the front panel of the bridge and the front terminals here or the front control interface of the scanners themselves. So now we're going to start a basic measurement with the 6625 system using a normal ohms configuration mode, which means sourcing current anywhere from basically about a microamp to 150 milliamps. And it's a 4-wire measurement, and we're going to choose a 10K resistance value here. We had wired this up just previously, and you can see here the 4-wire terminals C1, C2, P1, P2. You make sure the connections are good and secure. Always check your connections. It saves you a lot of trouble when you're diagnosing problems. And so that's connected now, so we use a 10K resistor. And what's important here is always make sure you check your channel. Here I've got channel 14, so I've got a 10K resistor, and I've connected it to channel 14. So this channel 14 wiring and labeling corresponds to the channel 14 that's here. So I am going to measure channel 14, which is lit right here. So now, for RS, and clear this scanner because we're not using anything that's on RS on this scanner, all of our RSs are here. These are our working references. And so, to measure this 10K, I'm going to measure it against a 10K resistor that's inside here. So, counting up, we have 1 ohm here, 10 ohm, 100 ohm, 1K, 10K. So this is my 10K on channel 21. And so now that this is illuminated, it tells me I've connected channel 21 to the RS terminals. And this is my known 10K resistor. So I'm going to have the bridge now make a comparison of our unknown resistor on this side to our known resistor inside the rack. and we'll be able to determine its exact value at this point. So here at the bridge, we're going to make a measurement through the front panel. And you're using the soft keys here. The first thing we're going to do is set up our test. So we start with setup, and we're going to edit an ohms measurement. Now, as mentioned before, we're going to do what we call normal ohms, which is sourcing current to measure anything from about 1 ohms to 100 k ohms. So we press normal, and we're into the edit menu. To get the cursor to come up, you press edit. You'll see the highlight comes up here and here, and now we can navigate through. And so resistance RS is the value connected to the RS side of our bridge. Now the RS side is typically our standard, which is inside the rack. And it's usually it's a known value. You would read the value off of your last calibration or through your trend analysis. And so it is 10,000.0264 ohms. And you would enter in its serial number, which this particular unit is 70694. And that would be read off of the back panel. And then you enter in your resistance for your RX. Now your RX is an unknown value, so you just enter in the nominal. You know it's about 10 k ohms. So you enter in 10,000. For this measurement, you would enter in 60 seconds. There is a table that is inside the operator's manual and in the software manual that outlines the best parameters for making measurements at various values with your RS and RX. Recommended that you almost tape it to the side of the rack. Keep it at hand at all times. It keeps your life very simple in terms of determining what are the best parameters for operation on the bridge. You want to be very careful about the operation parameters used in the bridge, because sourcing too much current into a resistor can cause damage to a standard resistor and absolutely destroys calibration and the history that it has. So when you're making a measurement for 10K, 10K, the recommended parameter is a 60-second reversal rate. What 60-second reversal rate means is that's when it's going to reverse the polarity from negative to positive to remove any thermal effects during the measurement. So every 60 seconds, what will happen is the polarity will change. And we're going to use a test current of 1 milliamp, which is the recommended. And that is usually based on power dissipation across the standard resistor of anywhere between 1 to 10 milliwatts. And we'll put the max current of 3.16, which is based on power dissipation of anywhere from 10 to 100, because anything past 100 milliwatts usually will damage the standard. So that's considered to be the highest you want to go in terms of a safe operation range. When you press OK, the values are all loaded and you're brought back to the menu. So you'll hit previous and previous again. This brings you back to the base menu. And then you enter into your measurement menu. In this area, you can basically start the measurement by pressing measure here, where it indicates that the measurement is currently off, and when you press it, it'll indicate that the measurement is on, and you can clear a buffer, because the bridge itself actually retains data from the last measurement inside a memory buffer that you can choose to clear every time you start a new measurement, or you can append to it in case you're doing maybe measurements on a resistor at different current levels, just to see the effect of the current and that sort of thing. You may wish to keep the data, but typically you don't. And essentially it'll begin its balance and start making a measurement. And that's how you start a measurement in normal ohms on the 6625 system. After the measurement has been running a little bit of time, you see that here that they've gone up to full resolution, and the bridge has an onboard statistical analysis and graphing functions built in so that you can actually monitor the tests as they're going along. So you go into the view menu, you have a couple different options. You got your detail and your graph and your summary. So we're gonna go and check the graph. And you check the graph, and essentially here shows the measurement and came in and now settled itself out. So at this point then we can tell that the measurement stabilized, and you've got your standard deviation, and it's just graphing as you go along here, right? So that being said, we're going to go into the summary. Now the summary is essentially, and then we go into our data summary. And essentially here we've made a bunch of measurements, and we've stabilized down to a very comfortable value, and it keeps the whole trend analysis of the entire measurement. However, what we're really interested in, of course, is the value once the resistance is settled into its comfortable spot. So what we would do here is we will clear the detail. And we hit confirm. What that does is it clears one of the buffers. So I still have all 190 samples here, and here I've only got one sample. And what this does is now we can back it out and take a look at it. We've got our measurements again. And again, if we look at the graph, in this graph, we only have a couple points. Very low standard deviation at this point because we've stabilized and we've settled in to our actual value that is going to be reported. And in the summary, of course, if I look at the summary graph, you'll still see that we have the whole history of the measurement where the initial balance and the resistor settling has come in. So the idea behind this is now you can actually go into your statistical analysis here and see that you've had your whole measurement trace, and then this is the value after it has stabilized. And this is the value here where you have your minimum, your maximum, your average, which is the one I would use to report on my actual certificate, and the standard deviation, which just shows the noise. And you can see here it's settled well into within a part per billion, which is 0.001 parts per million. So it's very stable at this point and has a good reading. And you can always hit refresh and updates. We've got into 9 samples and it's getting to be about 0.0027. And I would imagine after you've got enough data here, which usually about 35 samples or more is a good set of data for your statistics here in your detail, you'll be about 0.01 parts per million as a final reading. Yeah, so we're getting up to 0.06 now, so we're getting close to that. And essentially that's how you would analyze your results on the screen. And this graphing function works in normal ohms, high ohms, and in low ohms, and allows you to analyze the results from any one of the tests you make. And once you're done your test, essentially you reach over and you just press your measure off. And that ends the test. And the advantage to this graphical system as well is that even though I have stopped the test, all the data is still there. And it'll be stored in the bridge until you start the next test, in which case you can choose to clear that data, or you can actually add more to it. And that would be if, say, I was to run the same resistors, add another current, and I just want to see the effective current and see how much it moved the value by. That sort of thing. And that's it. That's how you make a measurement on the bridge. So now we're going to discuss how to make measurements in high ohms mode. So over here, I have the resistor I connected previously. It's a high ohms resistor. It's a 2-wire resistor, and it's at 10 mega ohms. And we're going to make a measurement on this one. In high ohms resistance, it's very important to use guarding. So make sure I plug my guard in this resistor. The guard terminal is right here. The guard terminal, of course, helps shield the resistor from EMI, with the metal shield around the outside. And also, there's guard that runs down all these SCW wires and stops leakage of different currents and voltages through the wires, which would offset this value. So this particular resistor is connected to channel 13, so I'm going to go and set this up to my RX as channel 13, and I'm going to choose a 1 mega ohm resistor as the resistor that I'm going to measure as my reference. So over on channel 13, that is my 10 meg resistor, and my 1 meg is on channel 23. So now I've connected my 1 meg resistor to RS, which is my known value, and my unknown 10 meg resistor over here on the table. Again, coming back to the bridge, I make a measurement here. We go into setup and edit ohms, and this time we're going to use high ohms, which in high ohms the bridge is sourcing voltage instead of current. And this is important to switch to a mode where you're sourcing voltage, because once you get to basically measuring at 100K, you're getting well below a milliamp of current, and it's very hard to have good resolution and stable currents at that low of a value. So it's easier to source voltage where you're going to be working with things like 10, 30, maybe 100 volts, which you can get much more commonly at a very stable value. So again, press edit on your RS, and we put in our 1 meg resistor, so 1 0 0 0 0 0 168 would be the number that is the known value for your resistor up here in the 6634. Again, the serial number 70694. And the RX resistor is essentially 10 megs. And you can also write using exponent notation. Instead of writing 10 with 7 zeros, you can just write 1e to the 7. And that's 10 megs as well. So if you know your scientific notation for your values, it saves you a couple keystrokes. Now the recommended reversal rate for this measurement is 120 seconds. It's much longer in high ohms values because of the fact that high ohms resistors typically have more parasitic effects and therefore take a lot longer to stabilize whenever you reverse the polarity of them. And this is essentially kind of like where you have a diode or a capacitor under different inductive effects that actually govern how this resistor settles. And so it takes a little longer when you reverse the current. And for voltage, when you put your voltage in here, the difference between current mode and voltage mode is in voltage mode, whatever you source as your voltage in here, that same voltage will be present on both the RS and RX sides. So you must choose the voltage based on the lowest value resistor. The lowest value resistor, I have 10 meg here and a 1 meg up here. My lowest value is my 1 meg resistor. And a safe operating voltage for 1 meg is 100 volts, which happens to be what the bridge is capable of producing anyway. So we're going to use 100 volts. I just wanted to point that out, so if you were using something like a 100K, you would only be able to go to 30 volts, or you would damage the 100K resistor. Again, those parameters are outlined in the manual, and you can find them in the appendix with the recommended test setups. So here we'll enter in 100 volts, and the max voltage will be 100 volts as well. Hit OK, come back to the menu, and previous. So then, the measure menu, you just press measure, and you're going to measure on to measure, and the measurement begins. And you can choose ratios or ohms, and you can see here that's basically measuring a nominally 10 meg ohm resistance. Lastly, what we're going to do is connect a low ohms value resistance measurement, and this is using, of course, the range extender here and a high resistance shunt. So essentially, what we have to do, if you take a look at our shunt here, and what we're measuring is a 0.05 ohm shunt. And I'm going to make a measurement at 10 amps with this shunt. So when we look at that, I'm going to connect to this range here, which allows me to go from 3 amps to 15 amps, which is the times 200 range. The important part about this is that you have to recognize the value your shunt is and the multiplier of this range. And that helps you choose the standard resistor we have to grab, or the 6634 here at the top. So if we take the value of this shunt, which is nominally 0.05 ohms, and we multiply it times 200, we come up with a value of 10. Which means that is the resistance standard we wish to use, is a resistance value of 10. You always want to keep it such that the resistance value that you're choosing happens to be slightly larger than or 1-to-1 that calculation found by the range extender. So in this example, I come up with the number 10, so the two standards that would be worth using would be a 10 ohm or a 100 ohm resistor. So I'm going to do it with a 10 ohm resistor. So the 10 ohm resistor is on channel 18. So we'll connect channel 18, and the shunt here is connected to channel 15. And so there's channel 15 there. And essentially now we go down to the bridge. And again, we go into setup, edit ohms, and we go into low ohms. Here is a way of changing different types of measurement modes for your range extender. We have a 6623A 300 range extender, and so we make sure we're on that one because we're choosing the profile. So that tells the bridge what kind of range extender we're actually working with. And again, we edit, and we have our 10 ohm resistor, which is 10.124. ohms, which would be read on the cert. Again, 70694 serial. Oops. You can go back and fix like that. 70694 for the serial number. Then the RX resistor is 0.05, which is the value of the shunt. We're going to make this measurement at 60 seconds. So the ratio entered here corresponds to the ratio that you have connected to on the range extender over here. And you see this is a times 200, which is the range we're using. So that has to be entered here on the bridge. So we'll enter in 200. And then we move to extender current, which is how much current the range extender itself is going to put in through the shunt, because at this point in time we are sourcing current from the range extender, and we're actually going to source 10 amps from the range extender. Last thing we have is the second screen here, and that has one extra parameter we need to define how much current is safe for RX, or for RS I should say, which is a 10 ohm resistor is 100 milliamps. We enter that and press OK. The test is loaded. We hit previous, previous once again. Back to the base menu, hit measure. And again, we toggle measure off, back to measure on. Clear the buffer, and then the measurement begins. And at this point in time, we're now making a measurement in low ohms using 10 amps from the range extender here through the shunt.